In this video, we'll be studying a new topic, or not a new topic related to electric dipole. It is electrostatic potential energy of electric dipole. Electrostatic potential of electric dipole in a uniform electric field. Right. Uh, so, firstly, we'll define what is your electrostatic potential energy is. So, you can define it as if a dipole is placed in a uniform electric field. If a dipole is placed in uniform electric field, okay, then uh, the work done, it is defined as the work done in rotating the dipole from a direction perpendicular to the field to a given direction. Okay, uh, this will be the work done. Okay, suppose this is your external field. Okay, right. Electric dipole is placed here. Then this electrostatic potential energy of the dipole is defined as if your dipole is something like this. That means the direction perpendicular to the field, and if you rotate this, okay, either in this direction, either in this direction, to the required one, and you need to know you want to know that what will be your electrostatic potential energy in this position. Okay, then uh, there's a formula. Okay, so that means this will be the work done required to rotate the dipole from a direction perpendicular to the field to the required direction where you want to know the electrostatic potential energy of the dipole system, right? If you rotate in this direction, sign will be something. If you rotate in direction opposite to it, then sign will be the opposite one. Okay, so we'll find that. Okay, numerically we'll find what is electrostatic potential energy of electric dipole, right? This is actually denoted as, okay. Before that, I would like to tell another formula to you. Just a sec. You need to calculate uh, work done on in rotating an electric dipole. Okay, explain. I'll tell you. Suppose electric dipole is placed in external electric field, right? And you need to calculate work done when electric dipole is moved from position theta 1 to theta 2, right? Suppose this is your electric dipole. Okay, and uh, it is kept here in your uniform electric field, minus charge, plus charge. Okay, and if you displace this dipole by a let's say smaller angle d theta, right? This angle is your d theta, right? Just a second. D theta. So you need to know what will be the work done, and then we'll integrate it. Okay, when dipole is placed at an angle theta, and dipole is placed with horizontal having angle theta, right? uh, in an electric field, dipole is placed at an angle theta. Okay, then torque due to electric field, it will do there will be a torque on the dipole due to electric field. Okay, then work done in rotating uh, the dipole from, let's say, theta to theta plus d theta. Okay, and that will be dw is equals to tau d theta. This will be the work done. It is similar to the when we do in work power energy, dw is equal to fdx. It is similar to this. Okay, so total work done, that means we'll need to integrate this total work done from theta 1 to theta 2. We are rotating the dipole from theta 1 to theta 2. Okay, so this will be w is equals to, and your torque will be E sin theta. This dipole is kept at an angle theta with the horizontal electric field, horizontal uniform electric field, right? D theta from theta 1 to theta. So W will be PE bracket, it will be uh, cos theta 1 minus cos theta. This is your final result. Work done in moving an electric dipole to from theta 1 to theta 2. Okay. If the dipole is initially in the direction of electric field, that means theta 1 will be 0. Okay. Initial condition. Okay. Means initially if dipole is aligned in the same direction as the direction of electric field, then theta 1 will be 0. So work done then will be what? It will be P 1 minus cos theta, theta 2 you can say, or theta. Okay. Now this is, you have got this formula. Okay. Now moving on to the previous slide, what I have defined you, the definition of electrostatic potential energy, that is defined as the work done in moving an electric dipole from a direction perpendicular to the electric field. That means initially your theta 1 is what? It is 90 degree, right? And we are rotating this dipole to our required position where we need to know the electrostatic potential energy. That means your theta final will be, right? So you just need to put this formula, put these in condition into your work done formula. Okay. So work done, which will also be the electrostatic potential energy, this will be equals to PE cos theta 1. Here your theta 1 is initially 90 degree. So cos 90 degree minus final condition is cos theta. We are moving it to theta. So this will be minus P cos. Your electrostatic potential energy will be minus P cos theta, and this can also be written as P dot vector minus P dot P. So we have got three results. Okay, three results. The first one in dipole, tau is equals to P sin theta. You need to know this. You need to note it. Okay, W is equals to P cos theta 1 minus cos theta 2, and the third one U is equals to P cos theta, cos theta. Right. These three are quite important formulas. Okay. So yeah, that's it from my side. In electric dipole, there are some extra topics. Okay, which you can on yourself do it. Okay, on your own. Okay. Let me. I think I have one more slide. I'll tell you that. That is force on electric dipole in non-uniform electric field. Here, all the cases are of uniform electric field, right? And if you see that if there is a non-uniform electric field, right, then how will you calculate the force? Okay, there are different cases. I'll tell you one special case. Okay, you can your own self you can create different cases, right? Let's say this is a dipole. Okay, dipole moment, right? There's another dipole minus q2 plus q is having dipole moments. Let's say p2, dipole moment p1, right? So E1 will be at the axis we are talking about 2 k p1 by r cube, right? At a distance r we are talking, means the electric field at this point due to this dipole, right? It, since they are lying on the axis. Okay, and E2 will be uh, means due to this it will similar be, but just you need to replace it by p2, right? And this distance is what? It is r. Okay, where we need to find the electric field. Okay, so your u will be what? That means electrostatic potential energy, it will be minus p2 to e1 to cos theta, means this dipole moment into electric field, that means due to this p1. Okay, into cos theta, means you can write it as 2 p1 p2 upon 4 pi epsilon naught r cube. Okay, Now force is what? This minus du by dr, means you need to differentiate it with respect to r. On differentiating it, you get force is equals to 2p1 p2 upon 4 pi epsilon naught ddr of r power minus 3. That will be, I think, 6p1 p2 minus के साथ. Okay, this will be 3 1 by r power 4. That means your force is inversely proportional to 1 upon r power 4, right? So in this way you can find out this is a one special case. Another case will be what? Your dipole is aligned something like this, something like this. This is your p1, this is your p2, and you need to find force. Okay, so for this dipole, this will be the equatorial position, and you can do it. Another case will be something like this. This is p1, this is p2. Okay, so something like this, you can find the forces on the other dipole due to the mass. So yeah, that's it from my side on the electrostatic. You need to practice problems as well. Okay.